Hello, so today we are going to look into clustering methods in machine learning. So what is cluster analysis? Where a cluster is a collection of data objects, okay? So they are similar to one another within the same cluster, and they are dissimilar from the other objects in the other clusters. Well, at least that's the goal when doing clustering, right? That's what we want to achieve. So basically, and the cluster analysis means, this process of grouping the objects into different clusters. It's an unsupervised technique, meaning there is no labels to use during this process. Okay, so there's no predefined classes. It can be used as a standalone tool to get insight into data distribution, basically trying to understand the patterns, the different clusters in the data. And also it can be used as a pre-processing step, meaning it can be applied and the cluster IDs, right, can be basically appended into the data and can be used as another information during the next phase of the analysis, which could be either classification or regression. So that's another use case of cluster analysis. So it's used in different areas like pattern recognition, image processing, document clustering, marketing, right, understanding customers, so many different areas of applications. For example, in land use, it can be used to identify areas of similar land use in an Earth observation database, like let's say satellite imagery and things like that. City planning, definitely useful, right, to understand which houses, which areas are similar to each other in terms of value, location, etc. Insurance, or basically customer analysis, right, to understand your customers better. And also, for example, in the insurance case, there's high risk customers, low risk customers, meaning people, high risk would be like people who tend to have more accidents, they are having more parking tickets maybe, or speeding tickets, and tickets where basically they don't even obey the basic rules, like putting your seatbelt on and things like that. So at the end, definitely useful for the company because they can lower the premium for those good customers and increase the premium for those who do not adhere to the rules. So what is a good clustering? So once we do the clustering, we want those items within the same cluster to be as similar as possible, while those other, the objects that are not the data points that are not within that cluster as different as possible. So this means there will be high intra-class similarity. So within cluster similarity is high, and the low inter-class similarity, meaning between cluster similarity, right? The similarity between the different classes should be low. So basically this is what we are looking for. So we want these points here within the same cluster to be as similar as possible. So low variance in a sense. And the interclass similarity to be low, right? We don't want these two clusters to be similar to each other. So that's the goal while doing clustering. Now, when we do clustering, basically we have to decide on how to define similarity, and that's defined by using different kind of distance matrix. So things like Euclidean distance can be used here, Manhattan distance, cosine distance, used in text data, for example. There's a variety of different distance matrix that can be used while working with, while doing clustering. So the partitioning method means, okay, how are we going to create these clusters? So there's different methods, different ideas for these. K-means is one of the most widely used ones, and in K-means, each cluster is represented by the center of the cluster. Center means the mean of the points are taken there. So the mean of the points that are within that cluster defines a cluster centroid, okay? Or the center of the cluster. K-medioids, or PAM, which is partition around medoids, is a bit different. There, each cluster is represented by one of the objects in the cluster. So in k-means, the cluster centroid is not necessarily present as a data point within the dataset. It is just the average of those points within the cluster there. But in k-medoids, it basically should be one of the data points within the dataset. So it can't be just the average, it should be present in the dataset as well. So when we look a bit closely into the k-means algorithm, the way it works is like this, okay? So we first have to define k. K means how many clusters are we going to create at the end. Is it 2 clusters, 3, 4, 5, 6, 100, how many? So we need to give that beforehand to the algorithm. So once that's given, once the k is decided, the method will start like so. So first it will partition the objects in the k non-empty subsets, and basically the k, the initial centroids are kind of randomly chosen. Okay, so and then basically it based on the distance, it basically assigns each of the points to the closest initial centroids there. So after that, right? So we have defined the cluster centroids, we have assigned all the points to those cluster centroids. Now is basically we will recalculate the centroid, because at the initial point, remember the centroid was assigned randomly. So since there is now points around them, we can actually calculate the cluster centroid. So the cluster centroid will be updated, and once the update is done, we will reassign points because the location will change of the centroid. So now the distances will change. So all the distances will be recalculated, and then reassignment will be done of the points. This process will repeat itself many times until there's no more change in the centroids and there's no more reassignment needed to be done. At that point, the algorithm stops. So for example, here, let's try to draw. So these 2 red points are the initial clusters. These are the closest points to this centroid over here, right? If you look at the distances, and these points are the closest points to this centroid here. Now, these red points were chosen randomly, so the assignment is done, and then we can recalculate the centroid of the light blue color points and these dark blue ones. So as you can see, the light blue color probably, the centroid should be somewhere around here maybe after this update, and I think the blue one should be somewhere around here, right? So that's what happens. So we will update the cluster. So you see the red point here, this initial cluster centroid, where the light blue color moves to here and this one moves here, and you see that the new updated centroids. Now we will reassign the points. So based on the distances, for example, this one probably is closer to the light blues now, the light blue central cluster. So this will be a new cluster here, and this will be the other cluster here. And then we will re-update, the centroids, and then reassignment will be done. And then it will continue like this until there is no more change. Let's look at it another way. So let's say these green data points are given to us, and the initial centroids are like those stars there. So we have decided to work with k equals 3 here. So when the first assignment is done, right, you can imagine these probably are closest to the gray star there. These probably, maybe these ones as well, are close to the yellow one, and I think these ones are close to blue. These ones probably, maybe some of them are yellow, and these ones are probably blue as well. So indeed, when you look at the left, right, we are assigning points. So this is the gray cluster, the orange or the yellow one, and this is blue. So now we will update the centroid. So this one will, the centroid of these points, all these ones are probably here. The yellow cluster, probably the centroid should be here, and the blue one should be around here. So this one will move here, this orange will move there, and blue will move there. Okay, so we have updated centroid. Now we will do reassignment. This one will not change, but the blue one, probably all these points, many of them, should go and become blue. Okay, and yeah, these ones will be yellow, something like that. So let's see how it goes. Yeah, indeed, these are the yellow cluster here. This is gray and this is blue. So again, the update will be done. This will move here. This probably will move closer to the, like the majority of the data points here. This one won't really change. That's what's happening there. And then reassignment of the points. So this is now the yellow cluster after the, after moving the centroid here. These points also will become blue, I think, and this will be the new blue cluster, and this will stay as is. And indeed, that's what's happening there. And then finally, we will update the centroid once more, but probably not much of a change will happen. And at this point, even if you do reassignment, right, all these points will stay with their colors, so no one will change. And at that point, the k-means algorithm will stop. So many times KNN is very, k-means and KNN are similar to each other, so many times we can confuse them. Basically, when we compare them, both models are distance-based, meaning we need to decide on, first of all, the k value, both in KNN and the k-means, and then also on the distance measured there. So that's similar behavior. However, KNN is supervised. Okay, that's very important, while k-means is unsupervised. So what does KNN do? It's basically, it uses the training data points, and the training data has labels, and it will use them to classify a new point. Right? In k-means, we're not doing classification. We're just trying to make as much use of the data to create different groups of data points together. This is not classification, okay? Because we don't have the class information available to us. And KNN is instance-based learning, right? Meaning all the data points are used in the training data to calculate all the distances, right? And then it was doing ranking, and then the first k values were chosen. Whereas the k-means only uses the k-centroid. So once the centroids are calculated, those points are not, at the end, once the clusters are settled, those points, the training points, are not used anymore. The only thing the algorithm needs to keep is the centroid. So only those centroids are used to assign a point to a cluster, right? When I go back here, at this stage, let's say a point comes and the point is right here, let's say. What the algorithm will do, it will look at the distance to this yellow cluster centroid, to the gray cluster centroid, and to the blue cluster centroid, and then it will assign this point to the one with the smallest distance, because small distance means more similar. So this will be assigned to this yellow cluster, so it will be like this. Okay, so that's how it works. So it doesn't look at the distances to these, every data point here, it doesn't look to any of them. Whereas KNN will look at those, so right, KNN is like that. Okay, to wrap it up with k-means, observations are clustered into k groups, where each observation is assigned to the group with the nearest centroid, the mean of the cluster. We need to decide on the k value, right? And we will talk a bit about this. So how can we decide on a good k value? We will look into that. The created clusters can be used as a feature for other algorithms, used in market segmentation, image segmentation, and many other areas. It's not very friendly with non-numerical data, similar to KNN, because of the distance calculation, right? It's more meaningful with numerical data. When you have non-numerical data, it becomes a bit more difficult here. And it's good when the groups are distinct and linearly separable, right? Because like this example here, like if you have points like, kind of distinct from each other like this, then it's much easier to work with k-means clustering, because it will be much easier for the k-means clustering method to find these clusters. But if there's too much overlap, too many points, and too much noise in the data, then it becomes much more difficult for k-means to find nice, good clusters there. All right, so that's the end, and we will work with coding next.